Greetings. This is the lecture, on the late side, but the lecture for Friday, October 21, in which we're going to solve some more phase diagram problems. I announced by email when I sent this out that we're going to have a quiz on Wednesday, again looking at kind of more advanced phase diagrams and slightly more advanced. And I will be out on Monday. So this is going to be the lecture for Friday, in which we solve some problems. So the first phase diagram that I want to look at is going to be this one. This is zoom in here a little bit. You can see it's the calcium chloride, lead, Cl2, and potassium chloride. And we talked about this phase diagram last week. What I want to do today is I just want to go through just a few more examples. And I'm traveling and happen to forget my ruler. So the good news is we will also learn how to approximate with paper. So let's pick a couple examples. So let's first pick someone with composition, say right here. Okay, so we start with that as our composition. We have to determine where it's going to wind up, and we do that by drawing out our compositional triangles, and also identifying the ternary points. So here is I'm going to change colors. There's a eutectic, and that eutectic corresponds to that, and that region. This region is potassium chloride. This is PbCl2,2KCl. So this looks as though this must be a mole fraction diagram. And you can get that because this is about 2/3 of the way through, and that's where the composition is. So then let's draw in, and this region is the calcium to chloride, which is again halfway through, so that tells us that it's mole fraction. Draw that in. That's a compositional triangle, so we know that we're in this compositional triangle and we have to go to that point, kind of for the sake of completeness, and so this corresponds to that liquidus surface. And kind of for the sake of completeness, let's draw a little bit more in. Not too much because we did most of this already. For the sake of completeness, let's identify that point. So that is 1 lead chloride, 2 potassium chloride. This area corresponds to 2 lead chloride, 1 potassium chloride, which means that this is this phase. Compositional triangle. Here. Great. Okay, so back to the problem at hand, that composition. So let's start out and just say, okay, what do we have as a function of temperature? Well, we start out, in order to be all liquid, we have to be over, whatever, 680 or so, right? Looking at the looking at the isotherms. We are in the region where we have the potassium chloride liquidus, which means then that as we cool, say down to 600, 600 is going to be that line. We get this tie line. That tie line we can approximate to be that. So composition, call this composition A. Composition A, we have, it looks like this. It doesn't seem to be. And I'll make my marker system. The pattern on this table. So we have about 4 those units to about 2, 3, 4, 4 and 4.3. 4.3. 3. That's 3 to 4.3. So the fraction liquid then is going to be fraction liquid is going to be 4.3 over 7.3. The fraction solid, which is pure KCl, is going to be 3 divided by 7.3. Okay, if we continue to cool, let's say we cool down to 550. We now pivot around our A point. Draw that in. The fraction, this is at 600, at 550, we have total line length of 1, 2, 3, 4, 5, 6, 7, 8. So fraction liquid is equal to 8. And using inverse level rule, that gives us about 3. And fraction solid is equal to, well, 5/8. This fraction solid, though, is broken up further, and that length, let's measure it out. That total length is is, let's see, 10, 20, 30, 32, and well, that's the total length. That's silly. Made a mistake there. We're actually not going all the way to the edge. We're only going to the point on our compositional triangle, which means that I should actually be measuring this distance. That point to this. That's going to be 10 and 11, 12, 13, 14, 15, 16, about 16.5. 16, oh, of course, it's halfway, right? So it was 32, should be about 16. That's about 16. And then this total length is 2. So it's going to be 2 16ths calcium chloride, 2 16ths CaCl2, and that makes it 14 16ths KCl. Okay, let's pick another example. Let's pick someone up here. So let's say we have a composition. Let's pick someone 640. Let's pick something here. Okay, so if we have someone there, let's look for the compositional triangles. The nearest eutectic is right down here. That eutectic corresponds to lead chloride and calcium chloride in there, and then calcium chloride, potassium chloride, which means actually this should be KCl, an ordered phase. Okay, which means we have this compositional triangle and that eutectic. So we start here. We are in the calcium chloride, potassium chloride ordered phase here. Let's say we cool down to 600. Well, if we cool down to 600, what happens is we start out here. We cool, we get our first liquid at 640. Go there. To that point. Let's try that in a little nicer, aren't we? There. We keep cooling down. Comes down to what I say. I said 600. So 600. So at 600, then we draw the tie line here. So there's where we got the liquidus. Okay. So now let's call this point B. Point B at 600. Point B at 600, we have a total tie line length of 1, 2, 3, 4, 5, 6, 7. Liquid. And using inverse lever rule, from point B to the edge, we have like around 1, 2, 3, 3.5. So that means the fraction of solid is going to be 3.5 also. Wow, look at that, 50-50. So 0.5, 0.5. Okay, the solid now though is composed of these two. And we know that total length is 16. So the solid is going to be fraction CaCl 2, and that's going to be 1, 2, 3, 3.5 divided by 16, right? Because we know that this distance from here to here is 16 from the previous part of the problem. And the fraction of CaCl2 KCl is going to be equal to 16 minus 12.5 divided by 16. And we'd also ask ourselves, what is the composition of the liquid? And the composition of the liquid, you could take it from this, or you could take it from drawing in the parallel lines here. We can do this just as well. Sorry, at that point. Here's, oh, Scott. There we go. That point. And that point. So we could read it from the compositional triangle. We could say then that, well, this is 16 liquid. It would be 16 divided by 1, 2, 3, 4, 4.5. So 4.5 over 16 PbCl2. 1, 2, 3, 4, 5, 6. 6 over 16 CaCl2 KCl plus, and that's going to be, what's going to be the difference between that, right? But it should be measured anyhow. 1, 2, 3, 4, 5. Should be 5.5 over 16 CaCl. So the composition of the liquid can be taken from the compositional triangle, or we could have taken it from the whole triangle. In this case, we don't have any of the markers on the edge, which makes it a little bit inconvenient. Okay. Another example, if we wanted to, or you know what? Let's skip to another diagram. This one's we've already done quite a few of the compositions. So let's pick one of the other diagrams from last time. So I was looking for a good example of a excuse me, a good example of a paratectic type transition, and most of the diagrams I showed you last time, there aren't really good examples built in. But here we have one, and actually we have two, and they're associated with having the sapphire phase, which is sitting out here, and the corderite phase. So let's look at these and look at the compositional triangles. So where we have corundum, molite, and spinel, that triple point, that's molite, spinel, corundum. So that gives us this compositional triangle. But then we have another point, another eutectic right here, and that is sapphire, which is in that little tiny triangle, sapphire, molite, and spinel. So sapphire, spinel, molite. So we have another compositional triangle. Which is this little one. It's here. And this is a good example now of a compositional triangle in which we have we can form a liquidus or a first solid that doesn't fit within the phase triangle. So for example, let's say, and that region occurs actually right in here. So for example, we could pick a composition. I'm going to pick a different color here. Let's get red. Let's pick a composition right here. So if we pick a composition right there, as we cool down, the first solid to form is corundum, because we're in above the corundum liquidus surface. And as we cool, so here's our temperatures, that's 1800. That is, numbers on that? That's 15, so this must be 1700, 16, yeah, that's 1700. And that makes that 1600, which makes that 1578, which is marked on the diagram. So as we cool down, we're going to form corundum. So at some point, say at 1800, like that, we could say that at 800, the fraction of liquid is maybe about 9.3, and the fraction of liquid here is going to be 1, 2, 3, 4, 5, 6, 7, about 7.5, and the fraction of solid is going to be what, 2.8. No, 1.8. 1.8 divided by 9.3. And this solid is pure Al2O3. If we keep cooling, we will eventually form a second solid here at that point, which is just slightly above 1700 degrees. We're going to have spinel, corundum, and liquid. And again, we can use the inverse lever rule to tell us what we have, and we can measure the composition of the liquid, just reading it off of the diagram. As we continue to cool, let's say we cool down to 1600, put this right there. We're moving along the along that valley, which means that we're using our original point as a pivot, which gives us an intersection right there, and this is spinel and corundum. So we use this region to denote our fraction of solid and liquid. So let's say at 1600 we have what do we have? Let's see. 10 11, 12, 13, 14. Fraction liquid. 14 divided by, here to here is going to be 1, 2, 3, 4, 5, 6, 7. 7 over 14, that means the fraction of solid is also 714 or 0.5. And then we talk about the solid. And the solid can be broken into corundum and spinel. Total length is 1, 2, 3, 4, 5, 6, 7, 8, 8.3. And spinel is going to be around 1.2 divided by 8.3. And that means the fraction of a corundum is going to be 7.1. Al2O3 and PIN spinel. Okay, but now we come to the eutectic point. Great. We continue, though, because we have to get down to this. We have to get down to this eutectic point, and this is not possibly the best diagram to look at, but we're going to work with it anyhow because it's what we've got. So let's say we stop at around 1500, which is going to be that point in the middle. Well, now we still use this as one end of our tie line. We still pivot around our composition, but now we draw our line to the spinel molite corner of the compositional triangle, and we're working with this compositional triangle here. So we have spinel molite. Let's just pick a different color here. Let's pick something very more visible. Say, let's pick green. So point there, point there. And that's it. So the interesting thing is, in the process of this, now we form liquid, right? Well, not a lot, I guess. Let's see what we got. Let's say at 1500. At 1500, the total length of the tie line is 1, 2, 3, 4, 5, 6, 7, 8. Fraction liquid is equal to 8, and that means that then this distance is about 0.7. Okay, so my mistake. We didn't form liquid, we actually got rid of liquid. So it's mostly solid, and then the fraction of solid is going to be 7.3 divided by 8. This solid is determined by the position there. So the fraction of molite, so the total length is 1, 2, 3, 4, 5, 6, 7, 8. The fraction of molite is that distance, so it's going to be 1, 2, 3, 4, 5, 5.5. Which means that the fraction of spin L is going to be given by 2.5 divided by 8. Great. And then we keep cooling down again. Not a particularly convenient diagram to work with, but the important thing is that as you look at the phases that are present, say spinel molite, that you recognize that you've transitioned from reading one compositional triangle to another. And there's really only one paratectic on this diagram. We could change the problem a little bit and say move our composition over here. And if we did that, then the process would be analogous, except that now we'd be coming down this side. So we'd have corundum and molite that form, and then the corundum has to be reabsorbed, and that allows for the formation of the sapphire. So the important point here, I guess, is that not only do we change compositional triangles, but in the process of changing compositional triangles, we have one of the phases, in this case the corundum, disappear, and that's what this makes this into a paratectic type diagram.